In the last video, we considered monochromatic signals, which looked something like this. It was a sinusoidal oscillation. And now we're going to talk about non-monochromatic but periodic signals, which we called multi-frequent signals. And these multi-frequent signals are periodic signals, but they do not have a sinusoidal pattern. They can look like this, or this was a triangle function, or it can be a rectangle function. So in what way do they differ from monochromatic signals? Both monochromatic signals and multi-frequent signals are periodic, and there is a relationship. So you can compose a multi-frequent signal out of many monochromatic signals. For example, let's consider the rectangle signal. In fact, you can prove that the rectangle signal consists of a superposition of an indefinite number of monochromatic signals, which relates in a very special way. So the first monochromatic signal is a monochromatic signal which with the same frequency as the rectangular signal, and then there are oscillations with 3 times the frequency. But weaker, and then 5 times the frequency, but even more weaker, and 7 times the frequency, and so on. So the rectangular signal can be composed of an indefinite number of monochromatic signals with multiples of the frequency of the rectangular signal, but not any multiple, only the odd multiples. So the rectangular signal is composed of a definite number of monochromatic signals with odd multiples of the base frequency of the rectangular signal. Yeah. So we considered it here, and now if you imagine that all those monochromatic signals superimpose, so let's for this example just consider the first 3 monochromatic signals. This looks something like this. Yeah, this already comes very close to our rectangular signal. But if you imagine that an indefinite number of the odd multiples of the monochromatic signals superimpose, then you get a perfect rectangular shape. And to describe this more mathematically, our periodic signal or periodic multi-frequent signal can be decomposed into an indefinite number of monochromatic signals. This is the form that we have learned in the previous video. So the monochromatic signal is a cosine function. Now we can see an interesting fact. So there is the base frequency, or here the base angular frequency. And this is the periodicity of the periodic signal. So it defines here the frequency at which the periodic pattern repeats. This is the base frequency here, and in this signal it is, where is it? It's here. Yeah, right. So this is the base angular frequency here in this formula, and the indefinite numbers of monochromatic signals which superimpose are not just of some random frequency. They are of multiples of the base angular frequency. Yeah. So this is why n is here in front of the base angular frequency, and n is actually our counting index. But you already notice that something is missing. So we had the phase in our monochromatic signal, but where is the phase here? The truth is that the phase is represented here by another set of functions which are also monochromatic. As we said, a monochromatic signal can be a cosine signal, but there's another function which fulfills the our condition of being monochromatic, and this is the sine function. And then this this second term here introduces the phase. So it's very similar as the first term. So the argument equals the argument here, but there's only a different function. But before we discuss what's about the cosine and sine function, there's something missing to complete our formula, and that is the A0 parameter. So that is just an DC offset. Imagine that you have a periodic signal. The A0 term just shifts our function in y-axis direction here. So this is 0. But now let's come back to the importance of the cosine and the sine function. What's about here? The cosine and sine function are orthogonal. But before we discuss this, let's mark this very important formula, which is called our Fourier series. It's you will also find the term Fourier analysis. This describes the process of decomposing any periodic signal into its monochromatic components. So you can decompose any multi-frequent signal, any periodic signal into its monochromatic components. And this is and the Fourier series is actually a description of composing the periodic signal out of its monochromatic components. Yeah. So this is the Fourier series is the inverse of the Fourier analysis. Yeah, Fourier analysis, decomposition, and the Fourier series is the composition of the periodic signal out of its monochromatic components. So now we can come back to the meaning of the cosine and the sine function. The sine function or the cosine function and the sine function are orthogonal. And orthogonality in general will be a very important term throughout this lecture. We will see it a lot of times, and it's very important. You know what orthogonal means. Imagine there's a Cartesian coordinate system with two axes, x and y, and both axes are orthogonal in a geometric sense and also in a mathematical sense, of course. In geometry, you know that two vectors with an angle of 90 degrees are orthogonal. And you know that, let's imagine we have two vectors, u and v. If they are orthogonal, their inner product is 0. This is the property of orthogonality. Or let's take an example here. U vector is 1, 0, and the v vector is 0, 1. So our inner product works so. The sine and cosine function are orthogonal. Let's come back to what we actually wanted to talk about. And you will find some additional information on orthogonality in chapter 2.2, which is the chapter where this video is based on. And as you know from mathematics, you can use orthogonal basis to construct any other value. So we use the two orthogonal bases, cosine and sine, of the cosine and sine function, to compose our periodic signal. And in the lecture notes you will also find the rules how to extract the coefficients in our Fourier series. So the Fourier series here, it has the coefficients a0, an, and bn, and the process of finding these coefficients is called the Fourier analysis. And you will find the formulas of for these coefficients in the lecture notes. I will just copy them from there. Oh. So those are the formula that we will also find in the lecture notes, and it is derived by using the orthogonality property of the sine and cosine functions. You see here prefactor, and then there's an integral which combines the periodic function, which should be analyzed, with either the cosine or sine function with the frequency defined here by the index n. And to visualize a bit more what's going on here, let's imagine that these two functions here are some kind of, let's call them test functions. So these functions take a measure of how much of the cosine part is inside the periodic signal with the specific frequency n omega 0. And the other function also tests how much of the sine function with the frequency n omega 0 is inside the periodic signal. So you can imagine that you have an analog radio, an FM radio, and then there is a frequency knob, and then you tune to a certain frequency and then listen how much signal is there, and then you measure the signal, for example, the strength of the signal, and just say, okay, here at n equals 1, there is the signal is this strong. And then you tune to another frequency to see, okay, the signal is this strong, and then you go to frequency 3, and of course it can be negative, and so on. So this is what in a figuratively way what these two functions do, and this also works for the B parameter. Now you take a, let's call it radio receiver for sine functions, and tune it to frequency 1, 2, 3, and 4. Then you get the values.